40 light-years away, a star barely larger than Jupiter is orbited by 7 worlds the size of Earth. One of them may have liquid water on its surface right now. Some of these planets are locked in place, one face burning in permanent daylight, the other frozen in permanent night. The star itself is dim enough that from one of its planets, it would look almost the size of a coin held at arm's length. Astronomers found this system almost by accident, using a telescope named after a Belgian beer. Radiation from the star may be stripping away atmospheres from the innermost worlds, even now. 3 of the 7 planets sit inside a zone where temperatures could, in theory, allow water to remain liquid. No one has confirmed an atmosphere on any of them. No one has ruled one out either. This is a story about the closest thing astronomers have found to a second solar system, and about how much remains unknown even after 10 years of watching it. This is Quiet Science at Bedtime. If this is your kind of story, a subscribe means everything right now. Everything described tonight is based on real scientific research, published data, and current astronomical understanding, current as of the most recent observations available. Just relax and feel free to let this play as you drift off to sleep. Now, let us begin. In 1999, a Belgian astronomer named Michael Guillon began building a small robotic telescope in Chile. Its purpose was narrow and specific, to stare at dim, cool stars and wait for tiny rhythmic dips in their light. A dip like that, repeating on a predictable schedule, would mean a planet was passing directly in front of its star, blocking a sliver of the star's glow as it crossed. The telescope was named TRAPPIST, an acronym for Transiting Planets and Planetesimals Small Telescope, and also a nod to the Trappist monks, known for their brewing tradition. It was a modest instrument by observatory standards, with a mirror just 60 centimeters across, but it was built for patience, designed to watch the same faint stars night after night for years, in a project that had little in common with the search for bright, dramatic targets. Before TRAPPIST-1, most exoplanet searches focused on sun-like stars, because brighter stars were easier to monitor with existing equipment. Guillon's approach was different. He reasoned that small, dim, low-mass stars, despite being harder to observe directly, would make it far easier to detect an Earth-sized planet crossing in front of them, because a small planet blocks a much larger fraction of a small star's light than it would of a larger one. In May 2016, Guillon's team announced they had found something orbiting a faint red star cataloged only as 2 Mass J 230629280502285. It would soon be renamed TRAPPIST-1 after the telescope that found it. At first, the data suggested 3 planets, each producing a distinct, repeating dip in the star's brightness. Something about the timing did not add up cleanly, though. The dips did not repeat in a way that matched only 3 orbits, and the team suspected the signal was more complicated than it first appeared. Follow-up observations began almost immediately, this time pulling in instruments far more powerful than the original 60-centimeter telescope in Chile. The Spitzer Space Telescope, orbiting the Sun in an Earth-trailing path, spent 20 consecutive days in September 2016 staring at nothing but TRAPPIST-1 uninterrupted. That kind of dedicated, continuous observation is rare. Most space telescopes divide their time across many different targets. Spitzer's 20-day campaign on a single obscure red dwarf reflected how seriously the initial three-planet signal had been taken. Ground-based observatories in Chile, Morocco, Hawaii, and the Canary Islands joined the effort, coordinating across time zones so the star was almost never left unwatched. As Earth rotated and one observatory lost sight of TRAPPIST-1 below the horizon, another, positioned further west, would pick up the watch. Together, these instruments logged close to 500 hours of combined observation time on a single dim red star, roughly the width of Jupiter. Some astronomers involved in the campaign have since described those months of overlapping observations as feeling less like a single discovery and more like slowly developing a photograph in a darkroom, where the full image only becomes legible after enough exposures accumulate. Individual transit events, viewed in isolation, revealed almost nothing certain about the system's true structure. It was only once dozens of overlapping light curves were laid side by side that the seven-planet architecture and its underlying resonance became unmistakable. By February 2017, the total count had risen from 3 planets to 7. All of them were roughly Earth-sized, ranging from about 0.77 to 1.13 times Earth's radius. All of them orbited a star so faint that it would be completely invisible to the unaided human eye, even from a planet only a few million kilometers away. The announcement was made public in a paper published in the journal Nature, co-authored by more than 30 scientists across multiple countries, reflecting how much international coordination the discovery had required. At the time, no other known star hosted this many roughly Earth-sized planets. A separate system, Kepler-90, held more total planets, 8 in all, but most of those worlds were far larger than Earth, closer in size to Neptune or Jupiter. TRAPPIST-1 was different specifically because of the size and number of its planets together, not simply the count. The announcement drew attention far beyond the usual astronomical community. NASA held a press conference on February 22, 2017, timed to coincide with the publication, and the story spread quickly through general news coverage worldwide. Part of that attention came from a simple, almost intuitive appeal. 7 planets, all roughly Earth's size, circling one star, was a scale of discovery that did not require a science background to find striking. Gillen's original team eventually grew to include researchers from the University of Liège in Belgium, the Massachusetts Institute of Technology, the University of Cambridge, and several other institutions across Europe and North America. Follow-up studies continued for years after the initial announcement, refining planet sizes, orbital periods, and density estimates as more data accumulated from repeated transit observations. That refinement mattered because early estimates of a planet's properties, based on limited data, often carry significant uncertainty. Each additional transit observed by a telescope adds precision to calculations of a planet's radius, its orbital period, and indirectly, its density and likely composition. Over nearly a decade of continued observation, the picture of the TRAPPIST-1 system has become considerably sharper than it was in that first 2017 announcement. 7 Earth-sized worlds, found circling a star too dim to see. The star at the center of this system belongs to a category astronomers call an ultracool red dwarf, sometimes classified more specifically as a spectral type M8V star. Its mass is only about 9% of the Sun's mass. Its surface temperature sits at roughly 2,566 degrees Celsius, several thousand degrees cooler than the Sun's surface, which burns at around 5,500 degrees Celsius. That temperature is worth sitting with for a moment. It is cooler than the melting point of iron, cooler even than some industrial furnaces used on Earth. And yet, despite burning at such comparatively low heat, TRAPPIST-1 still generates enough light and warmth to potentially support liquid water on planets orbiting close enough to it. In terms of physical size, TRAPPIST-1 is barely larger than the planet Jupiter, even though it contains roughly 80 to 90 times more mass than Jupiter does. This is possible because stellar material behaves differently from planetary material. Gravity compresses the star's hydrogen and helium into a state far denser than anything found in a gas giant's atmosphere, packing enormous mass into a comparatively small volume. Red dwarfs like TRAPPIST-1 are by far the most common type of star in the galaxy. Current estimates suggest they make up somewhere between 70 and 75% of all stars in the Milky Way, and yet because they are so dim, not a single one is visible to the unaided human eye from Earth, not even the nearest examples just a few light years away. This abundance is precisely why systems like TRAPPIST-1 matter so much to the broader search for life beyond Earth. If potentially habitable planets are common around red dwarfs specifically, then the sheer number of red dwarfs in the galaxy would mean far more potentially habitable worlds exist than if habitability were limited mostly to rarer sun-like stars. A single well-studied example, close enough and clear enough to examine in detail, becomes a template for understanding an entire dominant category of star. TRAPPIST-1 itself sits in the constellation Aquarius, roughly 40 light-years from Earth. 40 light-years is close by galactic standards, a near neighbor among the roughly 100 billion stars estimated to exist in the Milky Way. Its light has been traveling toward Earth for just over 4 decades. Aquarius is a faint constellation to begin with, difficult to trace from most brightly lit locations on Earth, and TRAPPIST-1 does nothing to make it easier to find. Even through a mid-sized amateur telescope, the star appears only as a barely there point of light, indistinguishable at a glance from countless other dim red dwarfs scattered across that patch of sky. Its scientific importance bears no relationship to its visual presence. This mismatch between visibility and significance is common throughout the search for exoplanets. The stars most likely to host detectable, potentially habitable worlds are often not the bright, easily photographed stars that dominate astronomy imagery, but the faint, overlooked ones that make up the vast majority of the galaxy's stellar population. When astronomers point their telescopes at it today, they are seeing the star and its planets almost exactly as they existed around the time the Voyager space probes were first launched from Earth in the late 1970s. Any change happening at TRAPPIST-1 right now will not be visible from Earth for another 40 years. Age estimates for the TRAPPIST-1 system have shifted as measurement techniques improved over time. Early estimates placed the system somewhere between 5.4 and 9.8 billion years old, an unusually wide range for a single stellar system. That range was so wide partly because red dwarfs age differently than stars like the Sun. A star like the Sun visibly brightens and swells as it burns through its core hydrogen, giving astronomers clear markers to estimate age. Red dwarfs change so slowly and subtly that pinning down their age requires indirect methods, including measuring how quickly the star rotates and how active its magnetic field appears to be. To put that uncertainty in illustrative terms, if TRAPPIST-1's age were a single human lifetime scaled up, the early 4 billion year estimate and the later 8 billion year estimate would be the difference between calling someone middle-aged and calling them elderly based only on a glance from a great distance rather than a direct medical exam. Narrowing that gap required something closer to a proper examination. Years of dedicated follow-up measurements, refining exactly how TRAPPIST-1's faint light was slowly changing over time. More recent analysis, using refined models of how red dwarfs cool and dim with age, has narrowed that estimate toward roughly 7.6 billion years. For comparison, the Sun and its solar system are approximately 4.6 billion years old. TRAPPIST-1 was already an old, established star when Earth's own solar system was still a swirling disk of gas and dust, not yet condensed into planets. This is not a young or chaotic system, still finding its final shape. It is ancient, and by most measures, remarkably stable. That stability connects directly to how red dwarfs burn fuel. Stars like the Sun consume their hydrogen relatively quickly, on a timescale of roughly 10 billion years, before exhausting their core fuel and beginning to change dramatically. Red dwarfs like TRAPPIST-1 burn far more slowly and efficiently, in part because their lower mass produces less internal pressure and a slower fusion rate at the core. Less pressure means a gentler, more prolonged burn, stretched across a timescale that dwarfs anything a Sun-like star will ever experience. Current models suggest TRAPPIST-1 could continue shining, largely unchanged in brightness and temperature, for another 10 trillion years. That figure is difficult to hold in the mind at any real scale. It is roughly 700 times longer than the current age of the entire universe, which is itself only about 13.8 billion years old. If any of TRAPPIST-1's 7 planets host conditions suitable for life, whatever form that might take, that life would have almost unimaginable spans of time in which to exist. There would be no equivalent to the eventual expansion and death of the Sun, an event expected to engulf Earth's inner solar system in roughly 5 billion years. TRAPPIST-1's story, on stellar timescales, is really only just beginning. But longevity does not mean calm. Ultracool dwarfs like TRAPPIST-1 are known for a very different kind of behavior, tied directly to their small size and low mass, frequent, intense flares, and bursts of high-energy radiation, far more common than anything the Sun produces on a comparable timescale. That volatile temperament, hidden inside a star that looks faint and quiet from a distance, becomes an important part of this story later on. For now, the 7 planets themselves deserve full attention. Their discovery represented something astronomers had never confirmed before: a single star hosting this many roughly Earth-sized worlds, packed into tightly spaced, precisely timed orbits. Nothing quite like it had turned up in over 2 decades of exoplanet surveys. The naming convention follows the order of discovery and orbital distance from the star. TRAPPIST-1 itself is treated as the A component of the system, following a naming standard used across exoplanet astronomy more broadly. The planets are labeled B through H, moving outward, with TRAPPIST-1b sitting closest to the star, and TRAPPIST-1h marking the outermost confirmed world. This letter-based naming avoids the kind of romantic or mythological labels used for Earth's own planets, favoring precision over narrative. TRAPPIST-1b completes a full orbit around its star in just over a day, roughly 1.5 Earth days. TRAPPIST-1h, at the outer edge of the confirmed system, takes closer to 19 days to complete a single circuit. For comparison, Earth takes 365 days to complete one orbit of the Sun. Every planet in the TRAPPIST-1 system completes its full year in less time than it takes Earth's own moon to complete one lunar cycle, which lasts about 27.3 days. An entire year on some of these worlds shorter than a single month on Earth. The full 7-planet system fits inside a region of space smaller than the distance between the Sun and Mercury, the innermost planet of Earth's own solar system. That entire 7-planet architecture would comfortably fit within the orbit of Mercury alone. Because TRAPPIST-1 is so faint compared to the Sun, planets can orbit that closely and still remain relatively cool enough that liquid water becomes a genuine physical possibility on at least a few of them. Proximity, in this case, does not automatically mean unbearable heat. This compact arrangement is part of what makes the system so unusual to astronomers. It is not simply the number of planets that stands out, but how tightly packed they are and how precisely their orbits interact with one another through gravity. Confirming all 7 required an extraordinary level of measurement precision. The transit method depends on detecting light dips of a fraction of a single percent, brief and subtle, buried within the ordinary flicker of starlight. With 7 overlapping orbital periods circling the same star, astronomers had to mathematically separate signals that blurred together in the raw data, distinguishing one planet's shadow from another's. It was, in a very literal sense, an exercise in untangling 7 overlapping rhythms from a single faint pulse of starlight. What emerged from that data was not simply a list of 7 separate planets. It was a system locked together by gravity in a way rarely observed anywhere else in the galaxy. The orbital periods of the 7 planets relate to each other through near-perfect mathematical ratios, a phenomenon astronomers call orbital resonance. Every planet's year fits into a precise numerical relationship with its neighbors, a pattern that repeats across the entire system. That resonance chain is so precise that scientists have used it to predict, with real accuracy, gravitational effects between planets before directly observing them, calculating where the system's rhythm required a particular kind of interaction to exist. Astronomers sometimes compare this kind of resonance chain to a slow planetary scale piece of clockwork, where each gear's rotation depends on the gears beside it. In TRAPPIST-1's case, that clockwork has apparently been ticking undisturbed for billions of years. Very few known planetary systems display resonance this extensive. Most systems, including Earth's own solar system, show only partial or approximate resonances between a small number of planets. A full chain linking all 7 bodies, as seen at TRAPPIST-1, is exceptionally rare in the current catalog of confirmed exoplanets. That rarity is part of why the system continues to draw sustained scientific attention nearly a decade after its discovery. It offers something close to a natural laboratory, a compact, stable, tightly interlinked set of Earth-sized worlds, all within reach of current and next-generation telescopes. Unlike many exoplanet discoveries, which involve a single distant world orbiting a star too faint or too far for meaningful follow-up, TRAPPIST-1 offered astronomers 7 targets at once, close enough and bright enough, relative to their star, for detailed study. That combination, quantity, proximity, and observability, is what elevated TRAPPIST-1 from an interesting find to one of the most closely studied planetary systems beyond Earth's own. Every one of the 7 planets carries its own distinct set of physical characteristics, its own size, its own density, its own position relative to the boundary where liquid water might survive. Some sit close enough to the star that surface temperatures likely soar past anything survivable. Others sit far enough out that ice may dominate the surface, if any atmosphere exists at all, to hold heat in place. In the years following the 2017 announcement, the discovery reshaped priorities across the broader field of exoplanet science. Several major observing programs shifted additional resources towards surveying red dwarf stars specifically, searching for other compact, resonant systems that might rival TRAPPIST-1 in scientific value. None found so far have matched it precisely, which has only deepened interest in understanding exactly how this particular system came to exist. Several near-miss candidates have emerged in the years since, systems with multiple transiting rocky planets around similarly faint stars, but none combine TRAPPIST-1's full set of qualities. 7 confirmed planets, a complete resonance chain linking all of them, and a star close enough and dim enough for detailed atmospheric study with current instruments. Whether that combination will ever be matched elsewhere remains an open question actively driving ongoing survey efforts. Researchers have proposed that the 7 planets did not form in their current tightly packed positions, but instead migrated inward over time, drifting closer to the star through gravitational interactions with the disk of gas and dust that once surrounded TRAPPIST-1 in its early history. As they migrated, the planets are thought to have locked into their resonant chain gradually, each new arrival settling into a stable rhythm with the worlds already in place. That formation story, still actively studied and refined, sets the stage for understanding the 7 planets as they exist today. It is this resonance, precise enough to have been predicted mathematically before every planet was even confirmed, stable enough to have persisted for roughly 7 billion years, that defines almost everything about how the 7 planets themselves came to be arranged the way they are today. The resonance chain linking TRAPPIST-1's 7 planets follows a precise numerical pattern. For every 2 orbits completed by TRAPPIST-1b, the innermost planet, TRAPPIST-1c completes almost exactly 1.25 orbits. That ratio continues outward, planet after planet, in a sequence astronomers describe using small whole numbers: 24, 15, 9, 6, 4, 3, in the relative periods of the 7 worlds, when scaled against each other. To put that pattern into everyday terms, imagine 7 runners on a circular track, each moving at a different but carefully matched speed, such that every time the fastest runner completes a fixed number of laps, each of the other 6 runners also completes a fixed, predictable number of laps, always the same ratio, lap after lap, without ever drifting out of sync. That is essentially what the 7 TRAPPIST-1 planets have been doing, gravitationally for billions of consecutive orbits. This is called a Laplace resonance, named after the 18th century mathematician Pierre-Simon Laplace, who first described similar orbital relationships among 3 of Jupiter's moons, Io, Europa, and Ganymede. TRAPPIST-1 is the first known planetary system where this kind of resonance chain extends across 7 separate bodies at once, rather than just 2 or 3. Laplace developed his description of resonance in the late 1700s, working purely from mathematics and telescope observations of Jupiter's largest moons, more than 2 centuries before anyone could confirm a planet orbiting another star at all. The fact that his equations apply almost directly to a system found 40 light-years away, around a star unlike anything in Earth's own solar system, reflects something durable about the underlying physics. Gravity behaves according to the same rules regardless of where in the galaxy it is observed. Confirming a 7-body resonance chain required more than simply measuring each planet's orbital period independently. Astronomers also needed to detect subtle timing variations, small delays, or advances in when each planet's transit occurred relative to a perfectly steady orbit. These variations, called transit timing variations, arise precisely because each planet tugs gravitationally on its neighbors, and measuring them gave researchers an independent way to estimate each planet's mass without needing to observe the star's own motion directly. 7 worlds moving to the same gravitational rhythm. The practical effect of this resonance is remarkable stability. In most planetary systems, small gravitational nudges between neighboring planets accumulate over millions of years, gradually shifting orbits until a system either settles into a new stable configuration or, in some cases, becomes chaotic enough that a planet is ejected entirely. TRAPPIST-1's resonance chain appears to actively resist that kind of drift. Because each planet's orbital period locks into a fixed ratio with its neighbors, gravitational tugs that might otherwise destabilize the system instead reinforce the existing rhythm, nudging any small deviation back toward the resonant pattern. Researchers have used computer simulations to test how long this configuration could last, and many models suggest the system could remain locked in resonance for billions of years, possibly extending across the entire remaining lifespan of the star itself. This kind of self-correcting stability is unusual enough that some researchers have proposed it as indirect evidence for how the system formed in the first place. A resonance chain this precise, involving 7 bodies simultaneously, is difficult to produce through random chance alone. Most current formation models suggest the planets migrated into these positions gradually, locking into resonance one at a time as each new world settled into the system from farther out, rather than forming already in their current tightly packed arrangement. That migration process is thought to have unfolded within the disk of leftover gas and dust still surrounding the young star, material that gradually dragged each forming planet inward through a subtle cumulative gravitational drag rather than any sudden or violent event. As each planet drifted inward and encountered the gravitational influence of the planet already ahead of it, the two would settle into a stable resonant ratio, effectively locking their relative rhythm in place before the next planet arrived to repeat the process with its own inward neighbor. Beyond stability, the resonance chain has also proven useful for something more immediately practical: prediction. Because each planet's orbital period is mathematically tied to its neighbors, astronomers can calculate precise transit timing years in advance, which matters enormously for scheduling limited and highly competitive telescope time on instruments like the James Webb Space Telescope. Knowing exactly when a planet will cross in front of its star, sometimes to within a matter of minutes, allows researchers to point expensive observing time only when it will actually capture a transit in progress. With that structural context established, each of the 7 planets can now be considered individually, moving outward from the star. TRAPPIST-1b, the innermost planet, orbits at a distance of roughly 1.7 million kilometers from its star, completing a full orbit in about 1.51 Earth days. For comparison, Mercury, the closest planet to the Sun, orbits at nearly 58 million kilometers, more than 30 times farther out. Despite that extreme proximity, TRAPPIST-1b likely does not experience runaway heat in the way a planet that close to a Sun-like star would, because TRAPPIST-1 itself emits so little energy overall. To imagine the view from such a planet, if TRAPPIST-1b's dayside surface were somehow observed directly, the star overhead would appear far larger in the sky than the sun ever appears from Earth, filling a substantial portion of the visible dome above, yet glowing a deep, muted red rather than the familiar white-yellow of the sun. This is an illustrative picture rather than a confirmed observation, since no instrument has actually photographed the planet's surface, but it helps convey just how differently a red dwarf's light would behave for anything standing beneath it. Even so, TRAPPIST-1b's estimated equilibrium temperature, a rough measure of surface heat assuming no atmosphere to trap or redistribute warmth, is estimated at well over 100 degrees Celsius, likely too hot to support liquid water on a permanently sunlit surface. Its density, based on mass and radius measurements, suggests a rocky composition broadly similar to Earth's, though some studies have proposed it may have lost most or all of any original atmosphere to radiation from the star. In 2023, observations using the James Webb Space Telescope's mid-infrared instrument measured the temperature difference between TRAPPIST-1b's dayside and nightside directly, an approach that does not require detecting an atmosphere at all, only measuring how heat is or is not distributed across the planet's surface. The results showed a stark contrast, consistent with little to no atmosphere, since a planet with a substantial atmosphere would be expected to redistribute heat more evenly between its two hemispheres. Bare rock, by comparison, retains almost no heat on its own and cools quickly once out of direct starlight. TRAPPIST-1's phi follows next, orbiting at roughly 2.3 million kilometers, completing its year in about 2.42 Earth days. Its size is close to Earth's, slightly smaller in radius, and its density suggests a rocky, iron-rich core, similar in proportion to Earth's own interior structure. Some atmospheric studies using the James Webb Space Telescope have suggested TRAPPIST-1's phi may have only a thin atmosphere, or none at all, though this remains an area of active investigation rather than settled fact. TRAPPIST-1d, the third planet outward, sits at approximately 3.2 million kilometers from the star, with an orbital period of about 4.05 Earth days. It is the smallest of the 7 planets by mass, at roughly 39% of Earth's mass, though close to Earth in physical radius. This mismatch between mass and size suggests a lower average density than Earth, hinting at a composition that may include a smaller iron core or a thicker layer of lighter material near the surface. That lighter material could take several forms, and current data cannot fully distinguish between them. Some researchers have proposed TRAPPIST-1d might carry a substantial water or ice content relative to its total mass, potentially forming a deep global ocean or ice layer beneath any atmosphere. Others have suggested the lower density could instead reflect a thinner rocky mantle with less iron overall, a compositional difference rather than a water-rich one. Distinguishing between these scenarios remains an open problem, dependent on future atmospheric measurements not yet available. TRAPPIST-1e arrives next, and it holds particular importance in ongoing habitability research. Orbiting at roughly 4.2 million kilometers, with a year lasting about 6.1 Earth days, TRAPPIST-1e is remarkably similar to Earth in both size and estimated density. Some early modeling has suggested it may be the single planet in the system most likely to retain a stable, long-term atmosphere, based on its distance from the star and estimated exposure to stellar radiation. Its estimated mass sits at approximately 0.69 times Earth's mass, and its radius at approximately 0.92 times Earth's radius, producing a bulk density close enough to Earth's own that some researchers have described it as the most Earth-like planet by density found anywhere to date among all confirmed exoplanets. Density alone cannot confirm habitability, but it does suggest a rocky, differentiated interior, broadly comparable in structure to Earth's core, mantle, and crust. TRAPPIST-1 follows, at a distance of roughly 5.5 million kilometers, completing an orbit in about 9.2 Earth days. It sits slightly beyond TRAPPIST-1e, still within the zone many researchers consider potentially favorable for liquid water, depending on atmospheric composition. Its estimated density is somewhat lower than Earth's, consistent with the possibility of substantial water or ice content relative to its total mass. If TRAPPIST-1F does carry a significant fraction of water by mass, models suggest it could take the form of a deep ocean layer, many kilometers thick, sitting atop a rocky core, rather than a thin surface ocean comparable to Earth's. At sufficient depth, pressure alone could keep water in exotic solid phases, even at temperatures where it would normally remain liquid closer to the surface, a structure with no direct equivalent among the rocky planets of Earth's own solar system. TRAPPIST-1G, the sixth planet outward, orbits at approximately 6.6 million kilometers, with a year of about 12.35 Earth days. It is the second largest planet in the system by radius, slightly bigger than Earth, and current estimates place it within or very near the outer edge of the zone where surface temperatures could, under the right atmospheric conditions, support liquid water. Its estimated mass is close to 1.15 times Earth's, making it, along with TRAPPIST-1F, among the more massive planets in the system. A planet this size, positioned at the cooler edge of the potentially habitable zone, presents a specific kind of scientific interest, a world where surface conditions could range from Earth-like to permanently frozen, depending almost entirely on how much heat any atmosphere is able to trap and hold near the surface. If TRAPPIST-1G does retain a substantial atmosphere, and if that atmosphere happens to include enough greenhouse gas to hold warmth near the surface, modeling suggests conditions that could plausibly resemble a permanently overcast, cold temperate climate rather than anything resembling a frozen wasteland. An entirely speculative but physically grounded picture rather than a confirmed one. Without such an atmosphere, the same planet would instead sit closer to the icy, airless character expected of its more distant neighbor, TRAPPIST-1H. TRAPPIST-1H, the outermost confirmed planet, orbits at roughly 9.0 million kilometers, completing a full year in about 18.77 Earth days. It is the smallest planet in the system by radius, and given its distance from the faint red star, its surface is likely far colder than any of its 6 neighbors, potentially cold enough that any surface water would exist only as ice. Its estimated equilibrium temperature sits well below the freezing point of water, drawing comparisons among researchers to Saturn's icy moon Enceladus, or to the outer reaches of Earth's own solar system, rather than to any of the rocky inner planets. Even so, TRAPPIST-1 has not been ruled out entirely as a subject of interest, since icy worlds elsewhere in the solar system have shown that subsurface liquid water can sometimes persist beneath a frozen crust, insulated and warmed by internal geological activity rather than by direct starlight. 7 distinct worlds, each shaped differently by its distance from a single dim star. Taken together, the 7 planets span a range of conditions from likely scorched and airless, in the case of the innermost world, to likely frozen and dim, in the case of the outermost. Three of them, E, F, and G, sit closest to the zone astronomers consider potentially habitable, a detail that will be explored in far greater depth later in this story. For now, a second defining feature of this system deserves attention: the physical relationship between each planet and its star, driven by gravity acting over billions of years, known as tidal locking. Tidal locking occurs when a smaller body's rotation gradually synchronizes with its orbital period around a larger body, caused by gravitational forces stretching the smaller body slightly out of a perfect sphere. That stretching creates a bulge, and the larger body's gravity pulls on that bulge, gradually slowing the smaller body's rotation until one side permanently faces the star and the other permanently faces away. Earth's own moon is tidally locked to Earth, which is why the same lunar face has always been visible from the ground throughout all of recorded human history. The mechanism that locked the moon to Earth over billions of years is the same basic physical process believed to affect most, if not all, of the 7 TRAPPIST-1 planets, due to their extremely close orbits around their star. The timescale required for tidal locking depends heavily on distance. The moon, orbiting Earth at an average of about 384,000 kilometers, took an estimated tens of millions of years to fully lock. The TRAPPIST-1 planets, by contrast, orbit their star at distances measured in millions of kilometers rather than hundreds of millions, placing them under tidal forces many times stronger than those acting on the moon. Under forces that strong, models suggest tidal locking at TRAPPIST-1 likely occurred within a few million years of planet formation, a comparatively brief span on astronomical timescales. Because all 7 planets orbit so near to TRAPPIST-1, the tidal forces acting on them are dramatically stronger than those acting on planets in Earth's own solar system. Current models suggest that most, and possibly all, of the 7 planets are either fully tidally locked or very close to it, meaning each likely has one hemisphere in permanent daylight and one hemisphere in permanent darkness. A planet locked in this way would experience no day-night cycle in the way Earth does. Instead, the boundary between the 2 hemispheres, sometimes called the terminator line, would remain fixed in place indefinitely, neither advancing nor retreating, separating permanent light from permanent dark along the same unmoving line year after year for as long as the lock persists. On Earth, the day-night cycle is driven by rotation on an axis, completing roughly once every 24 hours, regardless of orbital position. A tidally locked planet has no equivalent spin relative to its star. Its rotation period and orbital period become identical, which is precisely why one side always faces inward and the other always faces away, much like how the same side of the moon always faces Earth rather than rotating into view and out again. One hemisphere, forever lit, the other, forever dark. This kind of permanent division creates extreme and lasting temperature differences between a planet's 2 hemispheres, a phenomenon with no equivalent anywhere on Earth. The sunlit hemisphere would remain hot, continuously absorbing radiation without any nighttime cooling period. The dark hemisphere, cut off entirely from the star's light, could plunge to temperatures cold enough to freeze most atmospheric gases directly onto the surface. Some researchers have proposed that on a tidally locked planet with a sufficiently thick atmosphere, strong, persistent winds could form, driven by the extreme temperature contrast between hemispheres. These winds, in theory, could help redistribute heat from the permanently lit side toward the permanently dark side, potentially narrowing the temperature gap and creating a habitable band along the terminator line itself, where light and dark meet. That terminator zone, existing in twilight rather than full day or full night, has become a specific focus of habitability modeling for tidally locked planets like those at TRAPPIST-1. Rather than searching for Earth-like conditions across an entire planetary surface, some scientists have suggested that a narrow ring of moderate temperature wrapped around the boundary between light and dark might be the most promising location to consider. This idea, sometimes referred to as eyeball planet modeling, because of the resulting pattern of concentric temperature zones radiating outward from the substellar point, has become a standard framework for evaluating tidally locked worlds throughout the search for potentially habitable exoplanets, not only at TRAPPIST-1, but across the broader catalog of known red dwarf planetary systems. Whether any of TRAPPIST-1's 7 planets actually retain enough atmosphere to support this kind of heat redistribution remains one of the central open questions in current research. Without a sufficiently thick atmosphere, there would be no mechanism to soften the extremes, and the temperature gap between hemispheres could remain severe, with little or no transition zone at all. Computer models built to simulate tidally locked planets with varying atmospheric thicknesses have produced a wide range of possible outcomes. Some simulations, using atmospheres roughly comparable in density to Earth's, show winds strong enough to keep the night side from freezing entirely, with cloud formations concentrated heavily over the substellar point, the spot on the dayside hemisphere directly facing the star. Other simulations, using thinner atmospheres, show far less effective heat transport, producing a night side cold enough to freeze out much of whatever atmosphere existed in the first place. That last scenario describes a process called atmospheric collapse, where gases on the permanently dark hemisphere cool enough to condense and fall as frost or ice, gradually depleting the atmosphere on the day side as well, since gas continues moving from high pressure to low pressure across the whole planet. Over sufficient time, a planet caught in this cycle could end up with most of its atmosphere frozen onto the surface of its permanent night side, leaving the day side comparatively thin and dry by comparison. Which of these outcomes applies to any specific TRAPPIST-1 planet cannot be determined from orbital mechanics alone. It depends on factors still being measured directly: how much atmosphere a planet started with, how much has since escaped due to stellar radiation, and how effectively any remaining gas can circulate between hemispheres. Each of these factors ties back to the star itself and to the radiation environment its 7 planets have endured across roughly 7 billion years of shared history. Unlike the Sun, which burns in a relatively steady, predictable manner across similar timescales, ultracool red dwarfs like TRAPPIST-1 are known for a far more turbulent relationship with the planets orbiting closest to them, driven by magnetic activity that remains unusually intense even in old age. That question, whether these worlds have atmospheres thick enough to matter, and what those atmospheres might contain, depends entirely on what the star has been doing to them since they formed. The next part of the story turns to that relationship directly: the flares, the radiation, and what nearly a decade of observation has revealed about their impact on all 7 worlds. That relationship between star and planet begins with something more basic than flares or radiation: simple heat, and where enough of it arrives to keep water liquid rather than frozen solid or boiled away entirely. Astronomers call this region the habitable zone, sometimes informally the Goldilocks zone, the range of distances from a star where a planet's surface temperature could, under the right conditions, allow liquid water to persist. The boundaries of that zone depend on the star's total energy output, not on distance alone. A brighter star pushes its habitable zone farther out. A dimmer star pulls it in close. Because TRAPPIST-1 emits only a tiny fraction of the sun's energy, its entire habitable zone sits compressed into a narrow band, all of it closer to the star than Mercury sits to the sun. Astronomers typically define two versions of this zone: a conservative estimate based on well-understood physical limits for water loss and carbon dioxide condensation, and an optimistic estimate based on less certain but still physically plausible scenarios observed elsewhere, including on Venus and Mars earlier in their histories. For TRAPPIST-1, the conservative habitable zone spans roughly from 0.024 to 0.049 astronomical units from the star, a distance so small it would fit more than 20 times over within the orbit of Mercury around the Sun. An astronomical unit itself is defined as the average distance between Earth and the Sun, roughly 150 million kilometers. Expressing TRAPPIST-1's entire habitable zone as a fraction of that single familiar distance helps convey just how compressed the whole system really is. Even the outer edge of its most optimistic habitable zone sits closer to its star than Mercury sits to the Sun, a planet already considered scorched and inhospitable within Earth's own solar system. Within that compressed zone, 3 of the 7 planets stand out. TRAPPIST-1, E, F, and G all orbit close enough to receive energy levels broadly comparable to what Venus, Earth, and Mars receive from the Sun, respectively, adjusted for TRAPPIST-1's much lower total brightness. Of the 3, TRAPPIST-1e receives an amount of stellar energy closest to what Earth receives from the Sun, which is part of why it has become the single most closely studied planet in the system. Some published models extend the optimistic habitable zone slightly further, suggesting TRAPPIST-1d at the inner edge and TRAPPIST-1h at the outer edge could also fall within a broader range of conditions worth considering, depending on assumptions about cloud cover, atmospheric composition, and how efficiently heat might circulate around a tidally locked world. Under the most conservative definitions, however, the core habitable zone remains centered on E, F, and G. 3 worlds, positioned exactly where water could survive. Positioning alone, however, does not guarantee habitability. A planet can sit at the ideal distance from its star and still be lifeless, cold, and airless if it lacks a sufficient atmosphere to trap heat and maintain surface pressure. Mars offers a clear example within Earth's own solar system. It sits near the outer edge of the Sun's habitable zone, yet its thin atmosphere leaves its surface far too cold and its pressure far too low for liquid water to persist for long. Venus offers the opposite kind of cautionary example. It sits near the inner edge of the Sun's habitable zone, close enough that early in its history it may have hosted liquid water on its surface. A runaway greenhouse effect, likely triggered by increasing solar output over billions of years, eventually drove surface temperatures to roughly 465 degrees Celsius, hot enough to melt lead, under a dense, crushing atmosphere composed almost entirely of carbon dioxide. Habitable zone position, on its own, guarantees nothing. It only sets the range of distances worth investigating in detail. Determining whether any TRAPPIST-1 planet has retained an atmosphere at all has become one of the most ambitious observational efforts in modern astronomy. Since 2023, 10 separate research programs have devoted a combined total of roughly 290 hours of James Webb Space Telescope time, specifically to the TRAPPIST-1 system, part of a broader initiative called the Rocky Worlds Program, which is expected to eventually total around 500 hours of observation across several rocky exoplanets. To put that observing time in perspective, a single JWST observing hour is among the most competitively requested resources in modern astronomy, with proposals for the telescope's time typically oversubscribed by a factor of 6 or more each observing cycle. Committing close to 300 hours to a single planetary system before the survey has even concluded reflects how seriously the astronomical community has come to treat TRAPPIST-1 as a priority target rather than simply one interesting system among many. The method astronomers use depends on extraordinarily subtle measurements. As a planet passes in front of its star, called a transit, a small fraction of starlight passes through any atmosphere the planet might have, and different gases absorb light at specific identifiable wavelengths. By comparing the star's light with and without a planet's atmosphere in the path, researchers can, in principle, detect chemical fingerprints, water vapor, carbon dioxide, methane, hidden inside the spectrum. To picture the scale of that measurement, the amount of starlight altered by a planet's atmosphere during transit is often compared to the dimming caused by a single moth briefly passing in front of a distant lighthouse beam. The lighthouse's brightness barely changes to a nearby observer, yet a sufficiently sensitive instrument, positioned correctly and watching closely enough, could in principle still detect that faint momentary dip. A second method, called secondary eclipse or emission spectroscopy, measures a planet's own heat radiation as it passes directly behind its star and briefly disappears from view. Comparing the star's brightness just before and during that disappearance reveals how much infrared heat the planet itself was emitting, which in turn reveals how well or how poorly its surface holds and redistributes warmth, a strong clue to whether an atmosphere is present at all. Both methods share the same underlying difficulty. The signal being measured is extraordinarily small. A planet's atmospheric signature typically alters starlight by only a few dozen to a few hundred parts per million, a fraction so small that separating it from ordinary instrument noise, let alone from the star's own natural variability, requires repeated observations, careful statistical modeling, and, in many cases, still leaves room for more than one physical explanation to fit the same data. TRAPPIST-1b, the innermost and hottest of the 7 planets, was the first target of this campaign. In 2023, researchers led by Thomas Green analyzed 5 separate secondary eclipse observations using JWST's mid-infrared instrument, measuring the planet's dayside temperature with high precision. The results were consistent with a dark, airless rock in direct thermal equilibrium with its star, showing almost no heat redistribution from its permanently lit side to its permanently dark side. That first result matched a broader theoretical framework researchers had already developed for predicting which rocky planets should retain atmospheres at all, sometimes called the cosmic shoreline. The concept compares each planet's escape velocity, how fast an object must travel to break free of the planet's gravity, against the total radiation the planet receives from its star. Planets receiving intense radiation while also having relatively weak gravity tend to lose atmospheres over time, while planets with stronger gravity, lower radiation, or both tend to hold on to them, a pattern first identified among rocky worlds within Earth's own solar system and now being tested directly against TRAPPIST-1's 7 planets. That data ruled out both a Venus-like atmosphere and a thick oxygen-dominated atmosphere with significant carbon dioxide, to a confidence level exceeding 6 standard deviations, an unusually high degree of statistical certainty in exoplanet science. For nearly 2 years, TRAPPIST-1b stood as one of the clearest examples yet found of a bare rocky exoplanet, stripped of any substantial atmosphere. A follow-up reanalysis of the same 2023 data, using a self-consistent radiative model of how heat would move through different possible atmospheres, went even further. It found that atmospheres containing as little as 100 parts per million of carbon dioxide at pressures above roughly 0.3 bars could be ruled out to a confidence level of 3 standard deviations unless the atmosphere happened to lack any strong infrared absorbers altogether, an unusual and less likely composition. Then, in December 2024, a new analysis led by Elsa Ducrot complicated that picture. Combining observations at 2 different infrared wavelengths, both sensitive to carbon dioxide absorption, the team found the planet's surface showed no obvious signs of the kind of weathering a truly airless rock exposed to billions of years of radiation and micrometeorite impact might be expected to display. 2 possibilities emerged: ongoing geological activity such as volcanism actively resurfacing the planet, or a thin, hazy carbon dioxide atmosphere altering how heat radiates from the surface. Researchers were careful to note that the observations, spanning nearly 48 hours combined, were not long enough to settle the question definitively. TRAPPIST-1b remains, as of the most recent published analysis, an open case rather than a closed one, a reminder that even the closest, most thoroughly observed rocky exoplanet outside Earth's solar system can still resist a simple answer. That reversal from a confidently airless rock to an open and debated case within about 2 years illustrates something important about the pace of this research. Conclusions in exoplanet atmospheric science are rarely permanent on first publication. They are provisional, built from limited observing time on an extremely difficult target, and subject to revision as additional data or more refined analysis of existing data becomes available. TRAPPIST-1c, the second planet outward, received similar treatment. A team led by Sebastian Ziba measured its secondary eclipse depth using the same 15-micron carbon dioxide sensitive filter, obtaining a value of 421 parts per million with an uncertainty of about 94 parts per million. That precision was not quite sharp enough to conclusively distinguish between a bare rock and a planet with a thin atmosphere. The measurement was, however, precise enough to rule out a thick carbon dioxide atmosphere comparable to Venus's, an ultramafic bare rock surface, a dark iron and magnesium-rich rock type common in volcanic settings, remained fully consistent with the data. TRAPPIST-1c, receiving an amount of starlight roughly comparable to what Venus receives from the Sun, occupies a position where a runaway greenhouse effect, similar to the one that transformed Venus, remains a live possibility if any substantial atmosphere exists there at all. That comparison to Venus carries weight beyond simple coincidence of temperature. Venus, within Earth's own solar system, stands as the clearest known example of a rocky planet transformed by extreme, sustained greenhouse warming, its original surface conditions almost entirely erased by billions of years of atmospheric evolution gone in a hostile direction. If TRAPPIST-1c ever hosted a thick atmosphere, the same runaway process could plausibly have already run its course there, leaving behind whatever bare or altered surface current measurements are now struggling to characterize. Separate transmission spectroscopy observations of TRAPPIST-1c, conducted across 2 additional transits, likewise found no clear atmospheric features, though once again, significant contamination from the star's own surface activity limited how confidently any single atmospheric scenario could be excluded. As with TRAPPIST-1b, the overall pattern pointed toward a bare or nearly bare surface, without fully closing the door on thinner possibilities. TRAPPIST-1d, sitting just outside the hottest region of the system, was analyzed more recently using transmission spectroscopy rather than emission measurements. 2 transit observations produced a spectrum with no strong molecular absorption features, placing strict limits on the kinds of secondary atmospheres the planet could plausibly retain, though a range of thinner atmospheric scenarios could not be entirely excluded. TRAPPIST-1d occupies an interesting middle position in the system, receiving roughly the same amount of stellar energy that Earth receives from the Sun when measured strictly by installation, though its smaller mass and different assumed composition mean this comparison does not translate directly into Earth-like surface conditions. Its low measured density, discussed earlier in relation to its bulk composition, adds a layer of complexity. A planet with a smaller rocky core and thicker volatile layer might behave quite differently, atmospherically, than a purely rocky world receiving the same amount of starlight. One planet at a time, a picture forming from silence and faint signals. TRAPPIST-1e, positioned closest to true Earth-like insolation among all 7 planets, has drawn especially intense scrutiny. A 2025 study led by Anna Glidden analyzed transmission spectra collected across multiple transits, hoping to detect or rule out specific atmospheric compositions. The results were more ambiguous than researchers had hoped for. Every single observation showed clear evidence of stellar contamination, a term describing how dark star spots and bright magnetic regions on the star's own surface, rotating in and out of view, can distort the light passing near a transiting planet and mimic or mask genuine atmospheric signals. Because TRAPPIST-1 is a magnetically active star covered in these surface features, separating the planet's true atmospheric signal from the star's own noisy behavior has proven extraordinarily difficult. This effect, sometimes called the transit light source effect, occurs because the light a telescope measures during a transit is never purely starlight passing through a planet's atmosphere in isolation. It is starlight from whatever specific patch of stellar surface the planet happens to be crossing at that moment, which may be unusually dark, unusually bright, or unusually magnetically active compared to the star's average surface. Researchers have found that these surface irregularities can introduce signal variations of 200 to 300 parts per million between one observation and the next, a magnitude large enough to overwhelm or convincingly mimic genuine atmospheric absorption features. To address this, some research teams have begun using statistical modeling techniques, including a method called Gaussian process regression, to estimate and subtract the star's contribution before analyzing what remains for planetary signals. Others have proposed a more direct approach, observing closely spaced transits of 2 different planets that cross nearly the same track across the star's visible disk, on the reasoning that any spectral feature shared between both planets' data likely originates from the star itself rather than from either individual atmosphere. Despite that difficulty, some scenarios could still be ruled out. Venus-like and Mars-like atmospheres were disfavored by the data. Hydrogen-rich atmospheres containing traces of methane and carbon dioxide were excluded entirely. A nitrogen-dominated atmosphere, similar in bulk composition to Earth's own, with only trace amounts of methane and carbon dioxide, remained fully permitted by the current data, neither confirmed nor denied. Separate observations released in late 2025 added an intriguing, unresolved detail, a possible hint of methane in TRAPPIST-1E's spectrum. Researchers were careful to caution that the signal could just as easily originate from the star's own atmosphere rather than the planet's, given how thoroughly stellar contamination has complicated every observation of this system so far. TRAPPIST-1E also has a physical advantage over its inner neighbors because it sits farther from the star. It receives less of the X-ray and extreme ultraviolet radiation responsible for stripping atmospheres away, making it, on physical grounds alone, more likely than TRAPPIST-1b or c to have retained one. A tentative methane detection, if eventually confirmed and shown to genuinely originate from the planet rather than the star, would carry particular scientific weight. Methane is a molecule that breaks down relatively quickly under stellar radiation, meaning any methane detected in a planet's atmosphere generally needs a continuous source to replenish it, whether geological, chemical, or, in principle, biological. For now, the finding remains exactly what careful scientists call it, a hint, not a discovery, awaiting further observation to confirm or dismiss it. That caution resisting the pull toward a dramatic conclusion when the data only weakly supports it, characterizes the entire body of research into TRAPPIST-1's atmospheres so far. No detection announced to date has claimed definitive evidence of a thick atmosphere, and no result has definitively closed the door on one either for any of the 7 planets. The system remains, nearly a decade after its discovery, a genuine open question rather than a settled story. TRAPPIST-1F and TRAPPIST-1G, positioned at the cooler edge of the habitable zone, have received comparatively less direct atmospheric observations so far, though both remain priority targets within the ongoing Rocky Worlds program. Current scheduling suggests both planets will receive dedicated JWST observing time as the broader survey continues, extending the same transmission and emission techniques already applied to their inner neighbors. TRAPPIST-1H, the outermost and coldest planet, sits largely outside the conventional habitable zone altogether, though it has not been excluded entirely from scientific interest. Its low estimated surface temperature places it in a category more comparable to the icy moons of the outer solar system than to any potentially temperate world, making it a lower priority for atmospheric characterization compared to its 6 warmer neighbors, at least for now. Taken as a set, the varying priority given to each of the 7 planets reflects a broader principle in exoplanet science. Limited telescope time must be allocated where it is most likely to produce a meaningful result. A planet already strongly suspected to be a bare, airless rock offers less scientific return per hour of expensive observing time than a planet still genuinely uncertain, positioned at the most promising distance from its star. What emerges from all 7 planets, taken together, is not a single clear answer, but a spectrum of open possibilities, weighted by physical likelihood. The innermost worlds appear most consistent with bare, largely airless rock, worn down by billions of years of exposure. The outer, cooler worlds remain less thoroughly measured, but position alone makes atmospheric survival somewhat more plausible for them than for their scorched inner neighbors. Untangling the star's own signal from any given planet's atmosphere has become, in practice, one of the central technical challenges of this entire research effort. That challenge exists because TRAPPIST-1 is not a calm, steady background light source the way researchers might prefer. It is an active, magnetically turbulent star, covered in shifting spots and prone to sudden, powerful releases of radiation, behavior that stands in sharp contrast to the quiet, ancient stability that governs its planet's orbits. The same star capable of hosting a resonance chain stable for billions of years is also, on much shorter timescales, one of the more volatile and unpredictable objects astronomers regularly observe. That contradiction, extreme long-term orbital order paired with extreme short-term surface chaos, has shaped every one of the star's 7 planets since the system first settled into its current configuration. Understanding exactly how that turbulence works, how often it strikes, how intensely, and what it has likely done to 7 small worlds locked in permanent proximity to it, comes next. Red dwarfs like TRAPPIST-1 are in a sense permanently young in their behavior, even when ancient in age. Stars like the Sun settle into a relatively calm, predictable pattern of activity as they mature, with magnetic outbursts becoming less frequent over billions of years. Ultracool dwarfs remain magnetically active for a far longer portion of their extraordinarily long lives, meaning a 7-billion-year-old star like TRAPPIST-1 can still behave, in terms of raw magnetic turbulence, more like a young, restless star than an aged and settled one. That turbulence expresses itself most visibly through flares, sudden, localized releases of magnetic energy from the star's outer atmosphere, capable of brightening the star's emission at certain wavelengths by a factor of tens or even hundreds within minutes. A team led by Christian Vida, analyzing 80 days of continuous brightness data collected by the Kepler Space Telescope's K2 mission, identified 42 distinct flaring events on TRAPPIST-1 during that window, an average of roughly 1 strong flare every 2 days. These flares arise from the same underlying physical process responsible for flares on the Sun: the sudden release of energy stored in twisted, stressed magnetic field lines above the star's visible surface. When those field lines snap and reconnect into a simpler configuration, the excess energy is released explosively, accelerating charged particles and heating stellar plasma to extreme temperatures, in some cases briefly exceeding 10 million degrees Celsius within the flare itself. The specific mechanism is well understood from decades of solar observation, but red dwarfs like TRAPPIST-1 experience it more frequently, and relative to their overall faintness, with proportionally greater impact than the Sun does. A flare that would represent only a minor blip in the Sun's steady output can represent a dramatic temporary surge relative to a red dwarf's normally faint baseline brightness, making red dwarf flares disproportionately significant events for any orbiting planet. Separate research has examined not just how often TRAPPIST-1 flares, but how hot those flares actually burn. Analysis of 2 well-observed flare events found their temperatures somewhat lower than the values commonly assumed in earlier habitability models, which had generally borrowed flare temperature estimates from studies of other better-studied M-dwarf stars. A cooler flare temperature shifts the resulting radiation slightly away from the most biologically damaging wavelengths, a small but meaningful adjustment when modeling how much surface ultraviolet exposure a planet might actually receive during a flare event. A flare, on average, every couple of days. For comparison, the Sun produces flares of comparable relative strength far less frequently, and Earth sits roughly 150 million kilometers away, distant enough that even a powerful solar flare arrives considerably diminished by the time its radiation reaches Earth's orbit. The TRAPPIST-1 planets orbit at distances measured in a few million kilometers, some as close as 1.7 million kilometers from their star. At that proximity, A flare of comparable relative intensity delivers a dramatically larger dose of radiation to a planet's upper atmosphere than an equivalent solar flare delivers to Earth. Separate observations using NASA's Swift Observatory, monitoring TRAPPIST-1 in ultraviolet wavelengths over hundreds of kiloseconds of accumulated exposure time, captured additional flaring behavior consistent with the K2 findings, while also confirming that the star's flare rate appears to vary depending on which wavelength range is being monitored and when the observation takes place. Infrared monitoring using the Spitzer Space Telescope, by contrast, detected only 2 flares across 20 consecutive days of observation, a reminder that a star's activity level can look strikingly different depending on which part of its light is being measured. The most energetic of these flares can temporarily elevate the star's ultraviolet continuum emission to roughly 200 times its normal, quiet level. That kind of spike does not last long, typically only minutes to a few hours, but its cumulative effect across billions of consecutive years adds up to an immense total dose of high-energy radiation delivered to the innermost planets, far exceeding anything Earth has experienced from the Sun across its own history. This radiation matters because of what it does at the level of individual molecules in a planet's upper atmosphere. High-energy ultraviolet and X-ray photons carry enough energy to break apart molecular bonds and strip electrons from atoms, a process called photoionization. Once ionized, atmospheric particles become far more susceptible to being swept away entirely by the star's own outward-flowing stream of charged particles, known as the stellar wind. The stellar wind itself, a continuous outflow of charged particles launched from the star's outer atmosphere, behaves differently around a red dwarf than around a star like the Sun. Because TRAPPIST-1's planets orbit so close to their star, they sit within a region of significantly higher particle density and stronger magnetic field strength than any planet in Earth's own solar system experiences, intensifying the physical forces available to strip ionized gas away from a planet's upper atmosphere. Radiation, thin and invisible, slowly carrying a planet's air away into space. This escape process, sometimes called hydrodynamic escape or photoevaporation depending on the specific physical mechanism involved, can strip lighter gases, particularly hydrogen, away from a planet's atmosphere relatively quickly on astronomical timescales, sometimes within tens or hundreds of millions of years, under sufficiently intense radiation. Heavier molecules, including water vapor, carbon dioxide, and nitrogen, tend to resist escape more effectively, though sustained enough exposure can erode even these more stubborn components over billions of years. Hydrodynamic escape occurs when the upper atmosphere absorbs so much high-energy radiation that it heats dramatically and expands outward, with the outermost, lightest gas molecules gaining enough kinetic energy to overcome the planet's gravity entirely. In extreme cases, this expanding outflow can become dense enough to physically carry along heavier molecules that would otherwise remain gravitationally bound, a process sometimes described as heavier gases being dragged along for the ride by a bulk outward flow of lighter ones. For a planet like TRAPPIST-1b, orbiting at just 1.7 million kilometers from a magnetically active star, models suggest this kind of intense hydrodynamic escape could have been active for a substantial portion of the planet's early history, particularly during the star's more luminous, high-activity youth. That extended exposure, more than any single dramatic event, likely accounts for the bare or nearly bare surface conditions favored by current observational data. Researchers have used models combining atmospheric escape physics with estimates of TRAPPIST-1's total radiation output across its lifetime to estimate how much atmosphere its innermost planets have likely lost. For TRAPPIST-1b and C, the two hottest and most exposed worlds, cumulative estimates suggest the equivalent of many Earth oceans worth of water may have been stripped away over the system's roughly 7 billion year history if either planet started with an ocean's worth of water in the first place. These estimates rely on tracking a specific escape pathway relevant to water specifically, high-energy radiation splitting water vapor molecules high in the atmosphere into hydrogen and oxygen. The much lighter hydrogen atoms escape into space relatively easily, while the heavier oxygen can either escape more slowly over time or, in some proposed scenarios, become incorporated into surface rock through oxidation, effectively locking what was once atmospheric water into the planet's mineral crust rather than leaving a trace in the sky at all. That framing carries an important caveat. It describes what could plausibly have happened under sustained early life radiation exposure, not a certainty confirmed by direct observation of ancient conditions. Young stars, including young red dwarfs, are generally far more magnetically active and far more luminous in high-energy radiation than older, more settled versions of themselves. If TRAPPIST-1 followed a typical activity history for its stellar type, its radiation output during its first few 100 million years, while its planets were young and its planetary system was still settling into its current resonant configuration, would likely have been substantially more intense than the activity level observed today. This early, intense period is sometimes called the star's youthful high-activity phase, and it plays an outsized role in shaping a planet's long-term atmospheric fate. A planet that survives this early period with a meaningful atmosphere intact stands a reasonable chance of retaining at least some atmosphere afterward, since the star's overall activity level, while still elevated compared to the Sun, generally declines somewhat as the star ages further. A planet stripped bare during this early window, by contrast, would need some other mechanism, volcanic outgassing, cometary impacts delivering fresh volatile material, or some combination of both, to ever regain a substantial atmosphere later on. A planet's fate perhaps decided in its earliest few 100 million years. Distance from the star changes this calculation considerably across the 7 planets. TRAPPIST-1b and C, the two innermost worlds, receive the most intense radiation and face the steepest odds of long-term atmospheric survival, consistent with the largely bare rock interpretation discussed in relation to their JWST observations. TRAPPIST-1e, F, G, and H, positioned farther out, receive progressively less X-ray and extreme ultraviolet flux, improving their theoretical odds of holding on to at least a portion of any original atmosphere or of maintaining a secondary atmosphere replenished by ongoing internal geological activity. Quantifying that difference, researchers have estimated that TRAPPIST-1b receives roughly 4 times the total X-ray and extreme ultraviolet flux that TRAPPIST-1e receives, a substantial disparity given that both planets share the same star in the same roughly 7 billion year exposure window. That 4-fold difference compounds significantly over billions of years, meaning even planets within the same system, orbiting the same star, can end up with dramatically different atmospheric histories based on distance alone. A useful, if imperfect, comparison can be drawn to standing at different distances from a single campfire on a cold night. Someone sitting close enough to feel real heat also sits close enough to risk sparks and smoke reaching them directly, while someone farther back stays cooler, but also safer from the fire's more immediate hazards. TRAPPIST-1's 7 planets occupy exactly this kind of gradient, each one trading proximity-driven warmth against proximity-driven exposure to the star's more dangerous outbursts. That geological activity, if it exists at all on these planets, could plausibly be driven by the same resonance chain responsible for the system's remarkable orbital stability. Just as gravitational interactions between Jupiter's moons Io, Europa, and Ganymede generate intense internal heating through a process called tidal flexing, the 7 TRAPPIST-1 planets, locked in their own precise resonance chain, likely experience similar gravitational flexing from their neighbors, generating internal heat independent of anything the star provides directly. This means the same gravitational architecture responsible for holding the system together on the largest scale may also be quietly heating each planet's interior from within, a kind of built-in energy source, with no equivalent among the more loosely spaced, weakly interacting planets of Earth's own solar system. Io itself offers a striking demonstration of how powerful this effect can be. Trapped in resonance with Europa and Ganymede, Io experiences enough internal tidal heating to make it the most volcanically active body known anywhere in the solar system, with eruptions powerful enough to launch material hundreds of kilometers above its surface. If even a fraction of that mechanism operates within the TRAPPIST-1 system, some of its 7 planets could be geologically active in ways that continuously resupply atmospheric gases, even as stellar radiation works to strip them away from the opposite direction. Extending that comparison speculatively, if one imagines a TRAPPIST-1 planet experiencing Io-like tidal heating, its surface might plausibly display the kind of active, sulfur-tinted volcanic terrain seen on Io itself, dotted with ongoing eruptions and resurfaced on geologically short timescales. No direct observation currently supports this specific picture for any TRAPPIST-1 planet. It remains an illustrative extension of known physics rather than a confirmed description of any world in the system. Volcanic outgassing on Earth itself provides the working model for how this replenishment might operate elsewhere. Earth's earliest atmosphere is believed to have formed largely through volcanic activity, as molten rock rising from the interior released trapped gases, including water vapor, carbon dioxide, nitrogen, and sulfur compounds, into the surrounding environment. A tidally heated TRAPPIST-1 planet, geologically active enough, could in principle sustain a similar ongoing outgassing process across billions of years, continually adding fresh atmospheric material even as radiation strips existing material away. Whether this kind of balance actually exists on any specific TRAPPIST-1 planet remains speculative, grounded in physical plausibility rather than direct evidence. No current instrument can directly detect active volcanism on a rocky exoplanet 40 light-years away. Researchers instead look for indirect clues, including specific atmospheric gas combinations that would be difficult to explain without an ongoing geological source, a search technique closely related to the broader hunt for biosignatures explored later in this story. This creates a genuine tension at the heart of ongoing TRAPPIST-1 research, a tug-of-war between loss and replenishment, playing out simultaneously across 7 planets over a timescale of roughly 7 billion years. Whether any given planet ended up with a net gain, a net loss, or some precarious long-term balance between the two processes cannot currently be determined through modeling alone. It requires direct observation, the kind that JWST and future observatories are still in the process of collecting. Beyond atmospheric erosion, High-energy radiation carries a second, more direct consequence, this one relevant specifically to the question of surface habitability, rather than atmospheric survival. Ultraviolet radiation in certain wavelength ranges is capable of damaging biological molecules directly, including the kind of genetic material believed necessary for life as it exists on Earth. Models of TRAPPIST-1's ultraviolet environment suggest that a planet with a dense Earth-like atmosphere featuring a protective ozone layer could maintain surface ultraviolet conditions broadly comparable to present-day Earth. Without that protective layer, however, or with a substantially thinner or chemically different atmosphere, surface ultraviolet exposure on a TRAPPIST-1 planet could rise to levels hostile even to some of the most radiation-tolerant organisms known on Earth, including certain extremophile bacteria capable of surviving unusually harsh conditions in terrestrial environments. The presence or absence of ozone, itself dependent on the presence or absence of a sufficiently oxygen-rich atmosphere, becomes a critical, currently unknown variable in assessing whether any TRAPPIST-1 planet's surface, as opposed to its subsurface or ocean depths, could plausibly support life as currently understood. Earth's own ozone layer offers a useful point of comparison for how significant this protection actually is. Formed largely as a byproduct of photosynthetic life, releasing oxygen into the atmosphere over roughly 2 billion years, ozone now absorbs the vast majority of the sun's most damaging ultraviolet radiation before it ever reaches Earth's surface. A rocky planet lacking any equivalent oxygen-rich history would have no comparable shield, leaving its surface considerably more exposed to whatever ultraviolet radiation its star produces, flare activity included. This creates something of a chicken and egg problem specific to red dwarf systems like TRAPPIST-1. On Earth, oxygen-producing life gradually built the ozone layer that now protects surface organisms from ultraviolet damage. On a planet where surface conditions are too hostile for life to establish itself in the first place, that same protective buildup could never begin, regardless of how favorable the planet's distance from its star might otherwise be. Subsurface environments, shielded from direct radiation entirely, or deep ocean environments beneath a sufficiently thick water layer, remain the scenarios some researchers consider more plausible starting points for life on a world without an already established atmospheric shield. Not just whether air remains, but whether that air can shield what lives beneath it. One additional factor complicates this picture further. A planet's own magnetic field, if it has one, could provide meaningful protection against both atmospheric stripping and surface radiation exposure, largely independent of atmospheric thickness. Earth's magnetic field, generated by the churning motion of molten iron deep within its core, deflects much of the solar wind before it ever reaches the upper atmosphere, significantly reducing atmospheric erosion compared to an unprotected planet at the same distance from the Sun. Whether any of the 7 TRAPPIST-1 planets possess a similarly protective magnetic field remains entirely unknown, since detecting a distant rocky exoplanet's magnetic field directly lies well beyond current observational capability. Some researchers have proposed that intense tidal heating, of the kind potentially driving volcanic activity through the resonance chain discussed earlier, could also help sustain a molten convecting planetary core capable of generating a magnetic field, offering a plausible, if currently unverified, path toward some measure of protection. Some theoretical work has explored indirect ways a planetary magnetic field might eventually be detected around a star like TRAPPIST-1, including radio emission produced when a planet's magnetosphere interacts with the star's own stellar wind, a phenomenon already observed at Jupiter and weakly at Earth. No such radio signal has yet been detected from any TRAPPIST-1 planet, and current instruments remain far from sensitive enough to reliably attempt the search. But the technique represents one more avenue researchers hope future radio observatories might eventually open. Mars offers a cautionary counterexample from within Earth's own solar system. Evidence from surface magnetism, preserved in ancient Martian rock, suggests the planet once possessed a global magnetic field, generated by a churning molten core, much like Earth's own. That field appears to have shut down roughly 4 billion years ago, likely as Mars's smaller core cooled and solidified more quickly than Earth's, removing the internal motion needed to sustain a magnetic dynamo. Many researchers connect that magnetic shutdown directly to Mars's subsequent dramatic atmospheric loss, as the solar wind, no longer deflected, gradually stripped away much of what once may have been a thicker, warmer Martian atmosphere. A similar fate, magnetic field loss followed by accelerated atmospheric stripping, remains an entirely plausible scenario for one or more of the TRAPPIST-1 planets, particularly the smaller, less massive worlds in the system, where a molten, convecting core may prove harder to sustain over billions of years than on a larger, more massive planet. Without direct measurement, though, this remains an informed hypothesis rather than a confirmed detail of any specific planet's history. Taken together, this chapter of the TRAPPIST-1 story resists a simple, comforting summary. The star that makes liquid water theoretically possible on several of its planets, by virtue of its dimness and its compact, close-orbiting system, is the same star whose magnetic volatility poses one of the most serious threats to any atmosphere those planets might otherwise retain. Habitability in this system is not a single yes or no condition, but the outcome of a continuous billion-year contest between a star's given warmth and its given violence. Whether any of the 7 planets emerged from that contest with a stable, life-supporting environment intact is a question that cannot be answered by orbital mechanics or radiation modeling alone. It requires searching directly in whatever faint atmospheric signal survives for the specific chemical signs that life itself, if present, would be expected to leave behind. That search is already quietly underway. Detecting whether a planet has an atmosphere at all is only the first step in a much longer investigation. Even a confirmed atmosphere, rich in familiar gases, would not by itself answer the deeper question driving so much of this research: whether any process on that planet, biological or otherwise, is actively producing and sustaining those gases in a way inanimate chemistry alone could not explain. Astronomers call this kind of chemical evidence a biosignature, a gas or combination of gases detectable in a planet's atmosphere that would be difficult to explain or difficult to sustain over time without some biological process actively producing it. The concept does not require detecting an organism directly, which remains far beyond current or foreseeable technology at interstellar distances. It requires detecting the chemical exhaust that life, wherever it exists, tends to leave behind. The broader field distinguishes biosignatures from a related but separate category called technosignatures, which refer specifically to evidence of technology rather than biology, such as artificial light, industrial pollutants, or deliberate radio transmissions. TRAPPIST-1 research to date has focused almost entirely on biosignatures rather than technosignatures, reflecting both the greater scientific plausibility of simple microbial life compared to advanced technological civilizations, and the fact that current instruments are built specifically to detect atmospheric chemistry rather than artificial signals. Oxygen has historically been considered one of the most promising biosignature gases, largely because of Earth's own history. Free oxygen makes up roughly 21% of Earth's atmosphere today, almost entirely as a byproduct of photosynthetic organisms splitting water and carbon dioxide to build organic material, releasing oxygen as a waste product across roughly 2.5 billion years of accumulation. Without ongoing biological replenishment, oxygen tends to react quickly with rock, ocean, and other atmospheric gases, meaning a planet with abundant oxygen but no life would be expected to lose that oxygen relatively fast on a planetary timescale. Oxygen's strength as a candidate biosignature comes specifically from this combination of traits. It is chemically reactive, meaning it should not persist in large quantities without a continuous source, and its most efficient known source anywhere in the universe is photosynthesis. On Earth, before photosynthetic life evolved, the atmosphere contained essentially no free oxygen at all, remaining that way for roughly the first 2 billion years of the planet's 4.5 billion year history, a long stretch during which simpler forms of life were already present but had not yet begun producing oxygen at scale. That long delay is sometimes called the Great Oxidation Event's slow prelude, and it offers a useful reminder for any future TRAPPIST-1 observation. The presence of life does not guarantee the presence of a detectable oxygen signature. If any of the 7 planets host only simple, non-photosynthetic microbial life, comparable to Earth's own earliest billions of years, its atmosphere might show no oxygen at all, even while genuinely biological processes continue elsewhere in its chemistry. A negative oxygen result, in other words, would not necessarily mean a negative life result. A gas that, on Earth, exists almost entirely because something is alive to keep producing it. That relationship, however, is more complicated around red dwarfs like TRAPPIST-1 than it is around a star like the Sun. Researchers have identified several physical pathways by which a rocky planet orbiting an M-dwarf could accumulate substantial atmospheric oxygen without any biological activity involved at all, a phenomenon known as an oxygen false positive. This concern applies specifically and disproportionately to late-type M-dwarfs like TRAPPIST-1, distinguishing them from Sun-like stars in a way relevant to how future missions plan their target selection. Around F, G, and K-type stars, categories that include the Sun, abiotic oxygen accumulation through this particular pathway is considered far less likely, provided the planet retains enough other atmospheric gas to prevent oxygen from ever building up to problematic levels in the first place. That comparative robustness has directly influenced mission planning for at least one major upcoming observatory, which has prioritized searching for oxygen specifically on planets around Sun-like stars, precisely to sidestep the interpretive difficulties that systems like TRAPPIST-1 present. The most significant of these pathways traces back to the star's own early history. Red dwarfs take considerably longer than Sun-like stars to settle into their stable, main sequence burning phase, sometimes remaining unusually luminous and active for several 100 million years after formation. During that extended early period, a young rocky planet's water could be broken apart by intense ultraviolet radiation into hydrogen and oxygen, with the lighter hydrogen escaping into space far more easily than the heavier oxygen left behind. Under the right conditions, models suggest this process could leave a planet with an atmosphere containing tens or even hundreds of bars of oxygen, an amount potentially far exceeding Earth's own oxygen-rich atmosphere, entirely without a single living organism ever existing on the planet. Some of that oxygen would likely dissolve into a molten surface magma ocean during the planet's early hot phase and become locked away in the mantle rather than remaining in the atmosphere. But models indicate enough could plausibly persist in the atmosphere to create a genuinely misleading signal if oxygen alone were used as evidence of life. Researchers first raised serious concern about this specific false positive pathway in the early 2010s, well before TRAPPIST-1 itself had even been discovered, while studying general models of rocky planet formation around low-mass stars. The concern proved directly relevant once TRAPPIST-1's 7 planets were confirmed, since the system's ultracool host star and tightly packed, close-orbiting planets represent almost exactly the physical setup those earlier theoretical models had been describing. That timing carries its own quiet irony. The theoretical framework for doubting an oxygen detection around a star like TRAPPIST-1 existed years before any telescope had the sensitivity to actually attempt such a detection, meaning the field arrived prepared with skepticism already built in, rather than developing that skepticism reactively after an ambiguous or overhyped result. Few areas of exoplanet science can claim their caution predates their capability quite so cleanly. This is precisely why modern biosignature science has moved away from searching for any single gas in isolation towards searching for specific combinations of gases that are difficult to explain through any known abiotic pathway simultaneously. The most frequently cited example pairs oxygen or its related molecule ozone with methane. On a planet with active biology, methane-producing organisms and oxygen-producing organisms can coexist, continuously replenishing both gases, even though oxygen and methane react with each other and would otherwise disappear from the atmosphere within a matter of years to decades. Two gases that, together, are far harder to fake than either one alone. Reproducing that specific oxygen-methane combination abiotically has proven considerably more difficult for researchers to model than producing oxygen by itself. The photochemical pathways that generate abiotic oxygen around M dwarfs tend to actively destroy methane rather than allow it to accumulate alongside oxygen, since both gases interact readily under the same ultraviolet-rich conditions. A planet showing strong, persistent signals of both gases simultaneously would represent a considerably more compelling case for active biology than oxygen detected on its own. Some researchers have explored whether volatile material transferring between neighboring planets could itself create a false positive signal in a system as tightly packed as TRAPPIST-1, where atmospheric material escaping one world could conceivably drift toward and interact with a neighboring planet's atmosphere. A detailed 2022 study modeling exactly this scenario for the TRAPPIST-1 system found that the physical fluxes required to produce a detectable oxygen-methane false positive through this pathway would need to be more than 100 times larger than any plausible abiotic transfer rate, effectively ruling out interplanetary volatile transfer as a meaningful source of concern for this particular biosignature pairing. Researchers have also identified specific accompanying evidence that would help distinguish a genuine biosignature from a false positive. Carbon monoxide and carbon dioxide present together in an atmosphere while methane remains conspicuously absent would point strongly toward oxygen produced through the photochemical breakdown of carbon dioxide rather than through biology. Detecting these accompanying molecules or confirming their absence has become a standard part of how researchers now evaluate any candidate biosignature signal. This kind of contextual analysis, examining a full suite of atmospheric gases rather than searching for one target molecule in isolation, reflects a broader shift in how the field approaches the search for life over the past decade. Early biosignature science tended to treat oxygen almost as a singular marker, a kind of cosmic flag confirming biology wherever it appeared in sufficient quantity. Current practice treats oxygen instead as one data point among several, meaningful primarily in the context of everything else detectable in the same atmosphere. That shift extends beyond gas chemistry into the broader question of a planet's overall environmental context. Researchers now routinely factor in a planet's likely tidal locking status, its estimated interior heat budget, its position relative to the habitable zone's inner and outer edges, and its host star's specific flare and radiation history, before assigning much weight to any candidate biosignature at all. A promising gas combination detected on a planet already known to be scorched, airless, and stripped bare by stellar radiation would carry far less weight than the identical signal detected on a planet already suspected, on independent physical grounds, to have a reasonable chance of retaining a stable, temperate atmosphere. TRAPPIST-1e benefits directly from this kind of contextual reasoning, its position within the habitable zone, its density closely matching Earth's own, and its comparatively lower exposure to the star's most damaging early life radiation, discussed across earlier parts of this story, all combine to make it the single planet in the system where a future biosignature detection would carry the most immediate scientific weight, should one ever be confirmed. Stellar flares add a further layer of complexity specific to active red dwarfs like TRAPPIST-1. A single intense ultraviolet flare striking a carbon dioxide-rich atmosphere can trigger a temporary surge in abiotic ozone production, lasting from days to weeks after the flare itself has faded, depending on the surrounding atmospheric chemistry. A biosignature search that happened to observe a TRAPPIST-1 planet shortly after a major flare could, in principle, register a stronger ozone signal than the planet's typical baseline condition, another variable researchers must now account for when interpreting any single set of observations. Given TRAPPIST-1's flare rate of roughly once every 2 days, discussed in relation to its overall radiation environment, avoiding flare-influenced observations entirely would be difficult, if not practically impossible, over any extended observing campaign. Researchers instead account for this by modeling flare-driven photochemical variability directly, treating it as a known quantifiable source of noise to be subtracted from any candidate biosignature signal, rather than as an obstacle preventing detection altogether. This kind of careful layered accounting for every plausible confounding factor, stellar contamination, flare-driven chemistry, and abiotic oxygen production alike, represents the difference between a suggestive anomaly and a scientifically defensible claim. To illustrate how disruptive a single flare could be to an otherwise careful measurement, imagine trying to photograph a faint, distant candle flame while a much closer strobe light fires unpredictably every couple of days. Even a brief, well-timed flash from that strobe could wash out or distort the candle's image in a single exposure, regardless of how sensitive or well-aimed the camera itself is. TRAPPIST-1's flare behavior poses a broadly similar challenge for any instrument trying to hold a steady, uncontaminated view of a single planet's faint atmospheric signal. Beyond gas-based signatures, some researchers have proposed a complementary approach specific to planets with substantial liquid water, searching not for atmospheric chemistry, but for the reflected light signature of an ocean itself. Water absorbs and reflects light differently across different wavelengths than rock or ice does, and a planet with large open bodies of liquid water could, in principle, display a distinctive shift in brightness as it rotates or as its illuminated phase changes, a technique some call ocean glint detection, though it remains largely theoretical for planets as distant and faint as those at TRAPPIST-1. This glint effect works on the same basic optical principle as sunlight glaring off a lake or ocean when viewed from an airplane window, a bright mirror-like flash concentrated at a specific angle relative to the light source. Applied to a tidally locked TRAPPIST-1 planet, any ocean sitting near the permanent boundary between its lit and dark hemispheres could, in theory, produce a subtle, repeating brightness signature as the planet's orbital position shifts relative to Earth, distinct from the steadier reflectivity expected of dry rock or uniform cloud cover. Looking not just for the air a planet breathes, but for the shine of water on its surface. Applying all of this to TRAPPIST-1 directly, no confirmed biosignature has been detected on any of the system's 7 planets as of the most recent published research. The tentative methane hint reported for TRAPPIST-1e in late 2025, discussed earlier in this story, remains unconfirmed and possibly attributable to the star's own activity rather than the planet's atmosphere. No oxygen detection, confirmed or false positive, has been reported for any TRAPPIST-1 planet to date. It is worth pausing on what an unconfirmed hint actually means in practice, since the distinction matters for how a story like this one should be told honestly. An unconfirmed hint is not a coin flip between life and no life. It is closer to a single blurry photograph taken from very far away, one that might show something significant, might show an artifact of the camera itself, and will not resolve into a clear picture without considerably more film. That absence of a confirmed signal should not be mistaken for a negative result. Detecting a genuine biosignature requires first confirming that a planet has a substantial atmosphere at all, a question current data has not conclusively settled for any of the 7 planets. A useful analogy here is a medical test that has not yet been run, rather than one that has been run and come back negative. The absence of a diagnosis is not itself a clean bill of health. It simply means the necessary test has not yet been performed with sufficient sensitivity. TRAPPIST-1's 7 planets currently sit in exactly that position, untested in the fullest sense, not cleared. This sequencing, atmosphere first, detailed chemistry second, biosignature interpretation third, reflects both a practical and a methodological necessity. Practically, current instruments do not yet have the sensitivity to detect trace biosignature gases against the backdrop of an unconfirmed or poorly characterized atmosphere. The underlying atmospheric signal must first be established with reasonable confidence before any subtler chemical detail can be extracted from it. Methodologically, claiming a biosignature detection without first understanding a planet's basic atmospheric composition and its host star's radiation environment would leave researchers unable to distinguish a genuine biological signal from any number of the abiotic explanations already discussed. Only after establishing atmospheric composition with reasonable confidence could researchers meaningfully search within that atmosphere for the kind of gas combinations, oxygen paired with methane chief among them, that would constitute compelling evidence of biological activity. TRAPPIST-1's 7 planets, spread across a range of installation levels from scorched to frozen, offer researchers an unusually complete natural test case for refining exactly this sequence, planet by planet across a single well-studied system rather than piecing together fragments of evidence from many unrelated stars scattered across the galaxy. Researchers working on TRAPPIST-1e specifically have modeled what a genuine biosignature detection might eventually look like, using both current instruments and future ones still in development. Detailed simulations of TRAPPIST-1e's potential reflected and emitted light, modeled across both modern Earth-like and prebiotic Earth-like atmospheric scenarios, show that combined oxygen-methane and ozone-methane signatures should, in principle, be detectable using sufficiently powerful future telescopes alongside supporting climate indicators like carbon dioxide and water vapor. These simulations rely on modeling 5 distinct scenarios for how sunlight, or in this case starlight, would reflect off TRAPPIST-1e's surface: a cloudy, modern Earth-like world, a cloud-free version of the same, a cloudy ocean-covered planet with minimal exposed land, a planet entirely blanketed in cloud, and a simplified world with a fixed wavelength-independent reflectivity used as a baseline comparison. Each scenario produces a distinct predicted spectrum, giving researchers a detailed reference library to compare against whatever real observational data future telescopes eventually collect. Comparing predicted spectra against real data in this way allows researchers to work somewhat backward from theory to observation, narrowing down which of several plausible planetary scenarios best matches whatever signal actually arrives from 40 light-years away. A prebiotic, oxygen-poor, early Earth-like atmosphere would produce a measurably different spectral signature than a modern, oxygen-rich one, giving astronomers a meaningful way to distinguish between a planet that might host life today, one that might have hosted it in the past, and one that likely never has at all. The scientific standard for declaring an actual biosignature discovery, rather than a suggestive but ambiguous signal, remains deliberately conservative throughout this entire field. Researchers generally require not just detection of a promising gas or gas combination, but active exclusion of plausible abiotic explanations, ideally supported by multiple independent lines of evidence gathered across separate observations, before any finding would be considered a credible claim of extraterrestrial biology, rather than simply an interesting anomaly worth investigating further. This deliberately high bar has produced formal frameworks within the field for evaluating any candidate biosignature systematically. One widely referenced framework, developed through a series of community workshops bringing together astronomers, chemists, and biologists, walks through a step-by-step process. Confirming the detection itself is statistically robust, evaluating every known abiotic pathway that could produce the same signal, weighing the surrounding planetary and stellar context, and only then assigning a confidence level to any biological interpretation. Applying this kind of structured, skeptical framework consistently is part of what separates credible biosignature science from premature or overstated claims. That structured skepticism has already shaped how researchers discuss the tentative TRAPPIST-1e methane hint from late 2025. Rather than treating it as evidence of life, or even confirmed evidence of an atmosphere, the scientific community has treated it exactly as the evaluation framework demands, as a signal requiring further observation, active consideration of stellar contamination as a competing explanation, and no premature conclusion in either direction until considerably more data becomes available. That conservative standard reflects the weight of the underlying question rather than a lack of enthusiasm within the research community. A confirmed biosignature on any TRAPPIST-1 planet would represent one of the most significant scientific findings in human history, which is precisely why researchers insist on ruling out every plausible, non-biological explanation first, methodically, before allowing themselves to draw that conclusion. Whether any instrument will ever reach that level of certainty depends on what comes next. The telescopes now being built, and the ones already at work. Untangling a planet's genuine signal from its star's own interference has become such a persistent challenge across the TRAPPIST-1 system that addressing it directly has become a mission goal in its own right. NASA's Pandora spacecraft, a small satellite roughly the size of a household refrigerator, launched on January 11, 2026, was built specifically for this purpose, carrying a compact telescope designed to monitor a star's surface activity and a transiting planet's atmosphere simultaneously, rather than treating them as separate problems requiring separate observations. The mission represents a deliberate departure from the enormous flagship observatories that have dominated exoplanet astronomy in recent years. Rather than a billion-dollar instrument years in development, Pandora was selected in 2021 through NASA's Astrophysics Pioneers program, designed explicitly to fund smaller, faster, lower-cost missions capable of answering focused scientific questions without the extended timelines flagship telescopes typically require. Its entire budget and build time were a fraction of what a mission like JWST demanded, illustrating a broader trend in exoplanet science towards smaller, purpose-built instruments working alongside, rather than in place of, the larger observatories. Pandora's approach addresses the stellar contamination issue directly by observing the same star continuously for extended stretches, rather than only during brief transit windows. Watching a star's brightness and surface features change over weeks at a time allows researchers to build a detailed map of where a star's spots and bright magnetic regions sit and how they evolve, information that can then be subtracted more precisely from any given transit observation of a planet crossing in front of it. The spacecraft carries two instruments working in tandem: a visible light camera repurposed from spare James Webb Space Telescope hardware, and a compact Cassegrain telescope built specifically for this mission. Together, they allow Pandora to measure a star's surface activity and a transiting planet's atmospheric signal using the same instrument platform, at the same time removing much of the uncertainty that arises when combining data collected by entirely separate observatories on different schedules. Pandora launched successfully on January 11, 2026, aboard a SpaceX Falcon 9 rocket from Vandenberg Space Force Base in California, following a brief delay caused by a government shutdown the previous autumn. After a month of instrument commissioning and calibration, the spacecraft began its planned year of science operations, monitoring at least 20 exoplanet host stars in total, chosen specifically because their atmospheres remain difficult to characterize using transit spectroscopy alone. TRAPPIST-1 sits among Pandora's roughly 20 planned target stars during its first year of operations. Alongside Pandora, a small ultraviolet-focused CubeSat called SPARCS, short for Star Planet Activity Research CubeSat, launched on the same mission, built to monitor flare activity specifically on low-mass stars like TRAPPIST-1, adding continuous ultraviolet coverage to complement Pandora's visible and infrared measurements. SPARCS occupies a specific, complementary niche within this growing observational effort, where Pandora watches for the broad patterns of star spots and surface activity across visible and near-infrared wavelengths. SPARCS focuses specifically on the ultraviolet range, most directly responsible for driving atmospheric escape and photochemical false positive signals, the same physical processes discussed extensively earlier in this story. Combining data from both instruments gives researchers a more complete picture of TRAPPIST-1's activity across a wider range of wavelengths than either satellite could capture alone. Built at the shoebox scale typical of CubeSats, Sparks weighs only a few kilograms, yet carries a dedicated ultraviolet camera capable of monitoring stellar flares in real time, continuously, for extended stretches unavailable to larger, more heavily subscribed observatories like JWST. That combination of small size and long, uninterrupted watch time makes it particularly well suited to catching flare events as they happen, rather than piecing together their effects after the fact from occasional brief snapshots. A small satellite built for one job, telling starlight and planet light apart. Beyond these near-term missions, two much larger observatories are expected to reshape TRAPPIST-1 research over the coming decade. The first, the Habitable Worlds Observatory, is NASA's next planned flagship space telescope designed specifically to directly image and analyze the atmospheres of potentially habitable rocky exoplanets, using techniques considerably more advanced than the transit methods JWST currently relies on for this system. Direct imaging, the core technique planned for the Habitable Worlds Observatory, involves physically blocking out a star's overwhelming glare using a specialized instrument called a coronagraph, allowing the much fainter light reflected or emitted by an orbiting planet to be captured and analyzed on its own. This approach differs fundamentally from the transit method used throughout this story so far, which depends on a planet passing directly in front of its star as seen from Earth. Direct imaging works even for planets that never transit at all, dramatically expanding which nearby systems could eventually be studied in this kind of detail. The technical challenge involved in this kind of imaging is considerable. A star like TRAPPIST-1 outshines any of its planets by a factor of many millions to one, even accounting for the star's own faintness, meaning a coronagraph must suppress starlight with extraordinary precision, blocking out the star almost entirely, while still allowing the comparatively faint planetary signal sitting extremely close to it in apparent position to pass through undisturbed. Achieving that level of precision has driven years of dedicated technology development, including extensive testing on ground-based telescopes and smaller space missions, specifically to prove the underlying optical techniques before committing them to a flagship-scale observatory. Because TRAPPIST-1 sits so close to Earth, and because its planets orbit so tightly around such a faint, small star, the system remains a strong candidate for future direct imaging study, as well as continued transit observation, offering researchers two independent, complementary techniques for confirming whatever any single method might eventually detect. The second, the extremely large telescope, currently under construction by the European Southern Observatory in Chile's Atacama Desert, will feature a primary mirror roughly 39 meters across, dramatically larger than any optical telescope currently in operation. A mirror of that size gathers vastly more light than smaller instruments, and combined with high-resolution spectroscopy, is expected to allow detailed study of reflected starlight from rocky planets like those at TRAPPIST-1, potentially detecting combined biosignature pairs such as oxygen and methane directly in reflected light, rather than relying solely on the transit technique. To put that scale in perspective, a 39-meter mirror covers roughly the area of a small stadium field, built not from a single piece of glass, but from nearly 800 individual hexagonal segments, each precisely aligned and continuously adjusted to work together as one unified optical surface. Constructing an instrument of this size is itself a multi-decade engineering undertaking, with first observations anticipated later this decade, following years of segment production, testing, and installation at the observatory site, roughly 3,000 meters above sea level. The extremely large telescope's ground-based location carries both advantages and limitations compared to a space telescope like JWST. Being on the ground means the instrument can be serviced, upgraded, and maintained far more easily than any spacecraft, and its enormous mirror can be built at a scale simply impossible to launch into orbit intact. It must, however, contend with Earth's own atmosphere distorting incoming starlight, a challenge astronomers address using adaptive optics, a technology that rapidly adjusts the telescope's mirror shape many times per second to counteract atmospheric turbulence in real time. The Atacama Desert site was chosen specifically for its combination of high altitude, extremely low humidity, and minimal light pollution, conditions that together produce some of the clearest, most stable night skies anywhere on Earth's surface. Those same qualities have already drawn several other major observatories to the same general region of Chile, turning that stretch of desert into one of the most scientifically productive patches of ground on the planet, almost entirely because of what can be seen looking upward from it, rather than anything found in the ground itself. Researchers have already modeled what these future observations might reveal, running detailed simulations of TRAPPIST-1's predicted reflected light spectrum under several different possible atmospheric conditions, preparing the analytical groundwork years before the actual instrument becomes available. That kind of advanced preparation, building the interpretive framework before the data exists to interpret, has become standard practice throughout this field, ensuring that once a future telescope does collect a signal, researchers can immediately compare it against a library of physically grounded predictions, rather than starting the analysis from nothing. This preparatory work also helps researchers understand, in advance, roughly how much observing time a future instrument would need to reach a confident conclusion, information critical for planning how scarce telescope time gets allocated once these next-generation observatories finally become operational. Detecting a faint reflected light biosignature signal from a planet 40 light-years away, even with a much larger telescope than JWST, is expected to require accumulating light across many separate observations, potentially spanning months or years of cumulative exposure time on a single target. That kind of extended commitment underscores something worth sitting with directly, even with every upcoming instrument currently planned or under construction. A definitive answer about life at TRAPPIST-1, if one exists to be found at all, likely remains years, possibly decades away. This is not a story with an imminent resolution. It is a story still being written, one careful, incremental observation at a time, by a research community deliberately unwilling to rush past uncertainty toward a comforting but unsupported conclusion. The JWST Rocky Worlds program itself continues alongside these future missions, with its full 500-hour observing campaign still being carried out in stages across multiple observing cycles. TRAPPIST-1 F, G, and H, the three planets that have so far received less direct atmospheric scrutiny than their inner neighbors, remain scheduled targets within that ongoing effort, meaning the picture of this system will almost certainly continue sharpening even before any of the larger future observatories come online. This kind of staged multi-year observing strategy reflects how differently exoplanet science operates compared to a single dramatic discovery moment, where the original 2016 and 2017 announcements captured public attention almost overnight. The deeper work of actually characterizing 7 planetary atmospheres unfolds gradually, transit by transit, eclipse by eclipse, each individual observation adding only a small increment of certainty to an overall picture that takes years to come into focus. That gradual pace can feel, to an outside observer, almost anticlimactic compared to the excitement of the original discovery, but it reflects exactly how reliable scientific knowledge about a system this complex is meant to accumulate, not through a single decisive experiment, but through many independent, carefully cross-checked observations converging slowly on the same conclusion, each one closing off a few more of the possibilities that came before it. Ground-based monitoring continues in parallel as well. The Speculoos survey, a direct successor to the original TRAPPIST telescope network that first found this system in 2016 and 2017, continues watching TRAPPIST-1 and hundreds of other nearby ultracool dwarf stars, refining orbital parameters, monitoring for additional flare activity, and watching for any subtle timing variations that might reveal details about the system not yet captured by space-based instruments. Long-term timing precision matters more than it might first appear. Even tiny cumulative shifts in when each planet's transit occurs, tracked patiently over years of repeated ground-based observation, can reveal subtle gravitational interactions too small to detect in any single short, observing campaign. It is exactly this kind of patient, unglamorous, decade-spanning monitoring that first allowed researchers to confirm the system's resonance chain with real confidence, and it remains the quiet foundation supporting every flashier space-based discovery layered on top of it. Speculoos operates a network of robotic telescopes spread across multiple observatory sites, including locations in Chile, Morocco, and the Canary Islands, echoing the same international, round-the-clock coordination strategy that first confirmed all 7 TRAPPIST-1 planets back in 2017, where the original TRAPPIST telescope was a single 60-centimeter instrument. Speculoos represents a considerably expanded version of the same basic approach, scaled up to survey roughly 1,000 nearby ultracool dwarf stars for additional transiting rocky planets, using TRAPPIST-1 itself as the proof that such small, dim stars are worth watching so carefully. The same kind of small telescope that started this story, still watching 9 years later. Nearly a decade after its initial discovery, TRAPPIST-1 has become something closer to a long-term research subject than a single completed finding, more comparable to a specific well-studied ecosystem on Earth that scientists return to repeatedly over years than to a one-time observation logged and set aside. Each new observing cycle adds another layer of detail, another planet's atmosphere constrained a little further, another false positive scenario tested and either ruled out or left standing. Very few objects in the sky receive this kind of sustained, repeated attention from so many separate instruments and research teams simultaneously. Most confirmed exoplanets are observed intensively around the time of their discovery, and then largely set aside as astronomers move on to newer targets. TRAPPIST-1's continued relevance, nearly 10 years on, reflects how unusually much a single compact system can still teach the field, even after the initial excitement of discovery has long since faded from public attention. Looking back across everything gathered so far, a rough shape of the system has emerged, even without a final answer. A faint, ancient, magnetically restless star, anchors 7 Earth-sized worlds, locked together in a resonance chain, stable enough to have persisted for roughly 7 billion years, largely undisturbed. The innermost 2 planets appear most consistent with bare, radiation-scoured rock, their atmospheres likely stripped away, entirely or almost entirely, sometime during the star's early, more luminous youth. The middle planets, TRAPPIST-1d, E, and F, remain the system's most genuinely open questions, positioned where liquid water theoretically could survive, if enough atmosphere remains to make that survival possible. The outer 2, G and H, sit at the colder edge of that same zone and beyond it, less thoroughly measured so far but not excluded from ongoing interest, particularly given the possibility of subsurface warmth on worlds too cold for surface water alone. Every one of those conclusions carries the same honest qualifier attached throughout this story: current data, current models, current best estimate, subject to revision as more observing time accumulates. That qualifier is not a weakness in the science. It is the science working exactly as intended, refusing to claim more certainty than the evidence actually supports, one careful observation at a time. That accumulation of detail matters because TRAPPIST-1 has become, in a very real sense, a proving ground for an entire category of star. Roughly 3 out of every 4 stars in the Milky Way are red dwarfs similar in type to TRAPPIST-1, meaning whatever researchers ultimately learn about habitability, atmospheric survival, and biosignature detection at this one specific system will inform how astronomers interpret data from countless other, less thoroughly studied red dwarf systems scattered throughout the galaxy. This proving ground role extends beyond pure atmospheric science into methodology itself. Nearly every technique now used to model stellar contamination, evaluate false positive biosignature scenarios, and simulate tidally locked climate patterns for red dwarf planets has been developed, tested, or refined specifically using TRAPPIST-1 as the primary working example. Future discoveries around other red dwarf stars, wherever and whenever they occur, will very likely be interpreted using analytical frameworks first built and stress-tested against this particular 7-planet system. The system's compact scale has made this kind of intensive study possible in the first place. 7 planets, all transiting, all bright enough relative to their small dim star to produce measurable signals, all packed into a single well-timed resonance chain, represents a combination of circumstances astronomers may not encounter again for years, if ever, around another single star. For now, the honest scientific summary remains one of patient, ongoing uncertainty rather than resolution. No confirmed atmosphere has been detected on any of the 7 planets. No confirmed biosignature has been found. No planet has been declared definitively habitable or definitively lifeless. What exists instead is a steadily narrowing range of possibilities, each observing cycle, ruling certain scenarios out while leaving others standing, slowly closing in on an answer that may still be years away. 40 light years is not a short distance, even for light itself. Whatever has happened at TRAPPIST-1 since its light last left the star, arrived at Earth just this year, has already been unfolding for 4 decades before any telescope here recorded it. The star continues burning, quietly the way it has for roughly 7 billion years already. It will likely continue burning in much the same way for trillions of years still to come, largely indifferent to whatever instruments on a small, distant, rocky planet happen to be watching it at any given moment. 7 planets continue their locked, resonant orbits, the fastest completing a year in little more than a day, the slowest taking not much longer than 3 Earth weeks. That rhythm has held unbroken since long before Earth's own oceans existed, since long before anything resembling life had appeared anywhere in this galaxy that we know of. Some hemispheres remain in permanent daylight, others remain in permanent dark. The line between them has not moved, and by current understanding will not move for as long as this configuration holds. 7 worlds, still turning the same locked faces toward the same dim star. In, out. Whatever waits within any of those 7 atmospheres, whether water or ice or simply bare volcanic rock scoured by ultraviolet light, has been waiting there for longer than human civilization has existed to wonder about it. The resonance chain holds. The star flares and quiets and flares again. And 40 light years away, 7 small worlds continue turning, slowly, patiently, exactly as they have for 7 billion years. That is where this story rests tonight. Everything you heard tonight is real. TRAPPIST-1 is out there right now. If you enjoyed this journey through one of the most remarkable planetary systems ever found, consider subscribing to Quiet Science at Bedtime and tapping the notification bell so you never miss the next story. Sleep well.